But thanks, Anthony. Hi, everyone. Welcome to the GeoDAWG seminar series, and thank you for coming to the second seminar of our seminar series. Last month, we got to hear a really great talk by Tomoko Matsuo on AmGeo, and this month we are very excited for Nick Pedatella to present his work on WACCMX. Before jumping into the seminar series, I just wanted to give a few quick administrative announcements. I wanted to highlight our new website, which is the URL is at the top of this slide, where you can find more information about the GeoDAWG working group as well as the seminar series. And if you're interested in joining the discussion and getting more involved, please join our mailing list. There's a link here, but also on the site where you can join, and we send out information, important information about data assimilative methods in geospace, as well as seminar reminders and starting the discussion through that medium. And as well, there's also links on the website to our seminar schedule, which you can see below. We update that regularly, and the seminar next month is a little bit up in the air due to the proximity to AGU, but please check that regularly and look out for announcements and all the major newsletters to see if we'll be holding that in December. And otherwise, we'll be starting again in the new year. And as always, if you have comments, suggestions, or questions, there's also a way for you to contact us through a Google form on our website as well. So please feel free to input that information there as well. So now I'll pass it off to Anthony Sciola, who will introduce our speaker this month.
All right, so hi everyone, Anthony Sciola. Really quick, just a couple of house rules. Please keep yourself muted unless you're actively speaking. And if you have a question, if it's like a clarification question, feel free to raise your hand or put a question in the chat during the talk, and we will be monitoring both of those to call on you. And then we can save the bigger discussion questions for the end. And so with that, I'd like to introduce our speaker today, Nick Pedutella. He's a researcher at NCAR HAO. He got his PhD in aerospace engineering from the University of Colorado Boulder in 2011, and his BS from Penn State. His research interests include lower upper atmosphere coupling, remote sensing of the ionosphere, and as you could probably guess, numerical modeling and data assimilation. And today he's going to be telling us about data assimilation using the WACCMX model. So with that, thanks, Nick, for joining us this month and giving the talk, and the floor is yours.
Okay, thanks for introduction and opportunity to present the work. Let me share my screen. You can see the presentation?
Mm-hmm. Yes. It's showing, there we go, perfect.
It looks correct.
Mm-hmm. Yeah,
yeah, not reversed.
Yeah.
Okay. Yeah. So thanks again. As you said, I'll present today on work in the data assimilation in the WACCMX model. And before I begin, I just like thank a few people, sort of primary collaborators on the work I'll show in this talk. Jeff Anderson, also at NCAR. He's the primary developer of DART. Sabane Databarua and Lynn Harvey did a lot of the work for some of the results that I'll show. And then Chiting Su and Fezul Laskar are two postdocs who have been doing a lot of work on data assimilation recently with ICON and GOLD. Okay, so just briefly before I get into the most of the material, just a bit of background and motivation why we want to do data assimilation, specifically in a whole atmosphere model. And this is really, of course, one of the main reasons to do data assimilation is the desire to reproduce variability during a specific event, to look at as real as possible what is happening throughout the entire atmosphere. And this really comes from two primary issues. One being that observations are always going to be limited in scope, both in terms of what they're observing spatially and temporally, but also there's certain things that we want to know about the atmosphere that are just fundamentally difficult to observe. So through data assimilation, you can get some sense of the the properties of the atmosphere that are hard to observe. And of course, numerical simulations alone are always going to have some uncertainty with them because they're not constrained directly by observation. So though they can give global information, they're always going to have some uncertainty. So the idea, of course, with data assimilation is to statistically bring together the observation and the model to really get the best of kind of both cases, where you're constraining the model towards some reality, and that gives you more information than you can get from the observations alone. And there's several reasons we would want to do what I would call whole atmosphere data assimilation. So from the surface extending into upper thermosphere. One is just improved estimate of the atmospheric state. So we can do sort of fundamental science in the middle and upper atmosphere variability. Another question is to using data assimilation, we can get good observationally constrained initial conditions, which can be used then to investigate predictability of the middle and upper atmosphere. And really one main reason we want to do this in a whole atmosphere instead of just ionosphere thermosphere type of model is that we can then incorporate the ionosphere thermosphere variability due to lower atmospheric forcing within a physics-based forecasting system. And this is important to get better capture a lot of the day-to-day variability during solar minimum and solar quiet time periods that is largely due to the lower atmosphere. So an outline for the remainder of the talk, first I'll present some discussion of how data assimilation is kind of different in the lower versus upper atmosphere and how that has implications for whole atmosphere data assimilation. Then I'll briefly give an overview of WACCMX DART, which is the data assimilation system that we've developed with the whole atmosphere model. And then I'll show some results, some looking more in detail at sort of optimally assimilating upper atmospheric observation, and then a few more kind of scientific use cases of the model. First looking at mesosphere dynamics and chemistry, and then looking at predictability of variability in the middle and upper atmosphere during sudden stratosphere warmings. So there's a lot of differences between the lower atmosphere and upper atmosphere that have implications when we want to start doing data assimilation. So this essentially means we can't just adopt what has been done, methods used for numerical weather prediction in the troposphere. You can't just adopt that strictly and apply it then to the upper atmosphere. One, of course, is a thermosphere and ionosphere system is externally forced from the sun, the so-called forcing from above. But then there's also internal variability to the atmosphere in terms of waves propagating upward from below that also drive a lot of variability. And this essentially makes a thermosphere or ionosphere a bit more of a driven system than you would have in the lower atmosphere, where you can just rely on sort of chaotic divergence to create ensemble spread. The fact that it's driven needs to be accounted for in the data assimilation process itself in terms of accounting for variability that is coming from an external source and not just strictly internal to the system. Another aspect is the spatial and temporal scales are significantly different in the lower atmosphere compared to the upper atmosphere. This is a movie here from a high resolution model simulation. So the top panel here is the meridional wind at 100 kilometers, and the bottom panel here is the surface meridional wind. And these are playing, I should say, at the same temporal frequency. So despite the fact that they look drastically different in terms of how the flow is moving in these two, the time scale of the movement is the same, or I should say the movies are playing at the same speed. So at the surface, you can see the sort of synoptic scale flow. These large scale flows are moving quite slowly. And of course, there is some higher frequency variability in the lower atmosphere, but a lot of the global scale dynamics end up being on these sort of slower moving time scales and larger spatial scales. If we look at 100 kilometers altitude, you can see that everything is moving quite a lot faster compared to in the troposphere. So the fact that the time scales are significantly different and spatial scales as well also has some implications for how we want to do data assimilation in the upper atmosphere compared to how you would apply data assimilation in the lower atmosphere. And another issue that becomes important is the fact, especially if we're doing whole atmosphere assimilation, is the treatment of smaller scale waves within the model. So atmospheric gravity waves are an important sort of source of dynamical variability in the middle and upper atmosphere, and they're always going to be present. Here on the right is just an example above a thunderstorm where you see these concentric rings at about 90 kilometers altitude that are due to the gravity wave in the mesosphere driven by this convection. And these gravity waves that we have in the middle atmosphere and upper atmosphere drive a lot of the variability that we see in the middle atmosphere, and they're important for setting up both the sort of mean state as well as a lot of variability. So we know that these are present and they're an important part of the variability. But when we add adjustments due to data assimilation in the lower atmosphere, if they're unbalanced, sorry, something popped up here. If the adjustments are unbalanced in terms of the flow, then you're going to generate spurious small scale waves in the lower atmosphere. And then as these propagate upward, they'll obtain larger amplitudes and then dissipate. So if you add a lot of additional small scale waves through unbalanced data assimilation adjustments, this is going to introduce additional mixing, and this can have a significant impact on the composition of ionosphere and thermosphere. So really being able to effectively treat these small scale waves is an important issue in terms of doing especially whole atmosphere data assimilation. And another aspect that is significantly different between the lower atmosphere and upper atmosphere is the observing systems are quite a lot different. In the lower atmosphere, you have a fairly well-developed both operational and research observational framework that is really quite dense and gives you good global temporal and spatial coverage. Here is kind of just contrasting example. Here is the observations assimilated in a model that extends into the lower thermosphere, looking at the observations in the mesosphere on the left versus on the right in the stratosphere and troposphere. And these are just radiance channels in the stratosphere, troposphere. So this isn't even everything that is assimilated in the model. But you can see on the right here in the lower altitudes, you're essentially filling in everywhere with some observation constraint to the model. Whereas on the left, there's always going to be some gaps in where you have observations at one time point. So the observation system is not nearly as well developed. And this, I should say, is also including some research data. So if you're trying to do operationally, then you have even less observations available. And another thing, especially at higher altitudes in the ionosphere, really a lot of the data we have in ionosphere and thermosphere is primarily of the ionosphere electron density. And the electron density in the ionosphere is largely driven by the state of the thermosphere. So to have any sort of permanence in your adjustments in the electron density, you really have to adjust the state of the thermosphere as well. And that requires good information on the covariance information to use the electron density observation to then adjust the state of the thermosphere. So that's another aspect that's quite important to consider is that we want to really be able to adjust the state of thermosphere from ionospheric observations if we want to have any kind of persistence of the effects of the assimilation. So that's another thing that is important to consider. So putting all this together, there are a few kind of implications for whole atmosphere data assimilation that mean that we can't just take what has been developed and tailored towards numerical weather prediction in the lower atmosphere and use it for directly for a whole atmosphere data assimilation. One aspect, as I said, is the shorter timescales. The upper atmosphere tend to require much more rapid data assimilation. Typically, you would want to use at least 1 hour cycling of the data assimilation, perhaps even faster, may be desirable during some time periods. The fact that it's externally driven by solar and geomagnetic activity, this needs to be considered, especially if you're using an ensemble approach in terms of generating the ensemble. You need to account for this fact that the system is externally driven to have a sufficient spread in the model ensemble to effectively assimilate observations. And then, as I mentioned, we also need to mitigate generation of small scale waves while also preserving real waves in order to really maintain the variability that is driven by waves throughout the entire atmosphere without excessively damping waves that are truly present. So there's sort of a balance there between not producing too many new waves, but also not just damping so much that you remove real variability. And then finally, because we have all these ionospheric observations in the upper atmosphere, we need to accurately represent the covariance between ionosphere and thermosphere in order to correctly sort of adjust the thermospheric state to be consistent with the ionosphere in order for the data assimilation to sort of have a longer impact in time. That significantly will help. So now moving on, I'll discuss the data assimilation system we've developed for a whole atmosphere model, which is this WACCMX DART model. And the background model for this data assimilation is the whole atmosphere community climate model with the thermosphere-ionosphere extension, so-called WACCMX. And this extends from the surface all the way to the upper thermosphere. And WACCMX is built on top of the WACCM model, which is in turn built on top of the atmospheric component of the community Earth system model, which is an Earth system model used for things such as climate prediction and other aspects as well. But so this is an Earth system model, not necessarily a numerical weather prediction model. So it's tuned more towards climate versus weather, which has some implications for how well you'd be able to do your data assimilation in the troposphere, because it's a climate model, not a weather model. And there's some differences there that are relevant. But this model, so it extends from the surface up to the upper thermosphere and includes interactive chemistry, including ion chemistry at higher altitudes. And of course, includes all the troposphere and stratosphere processes that come with an Earth system model that is used for studying the Earth's climate. It, of course, includes then solar variability, and then also self-consistent electrodynamics as well as F-region transport. And WACCMX enables us to study the variability due to both lower atmosphere as well as solar and geomagnetic forcing. And those who are maybe familiar with other models such as TIE-GCM, WACCMX essentially adopts a lot of the processes from TIE-GCM and builds them into this framework, but it extends to much lower altitude than TIE-GCM would. And the data assimilation that is used here in the model, it comes from the DART, which is a data assimilation research testbed. And this is an ensemble Kalman filter approach. So at each time step, we have a set of observations, where then we have the data assimilation. And this produces a whole set, basically an ensemble the analysis fields, and then we run all of those forward in time in the data assimilation forecast step, and then combine with the observations at the next time step, and continually repeat this. And since this is ensemble approach, we will always have a full set of analysis fields and then also forecast fields. One of the advantages of the ensemble approach is that we don't need to specify the background covariance information sort of prior to the doing the data assimilation, because it can be obtained directly from the ensemble of model simulations. And this is significantly advantageous because the covariance information in the upper atmosphere is I don't think very well quantified at the moment, and also is likely highly variable. So being able to use the ensemble to get that covariance information is significantly advantageous, I would say, in terms of, like I said, using the ionosphere information to adjust the thermospheric state. And as I mentioned in introduction, by using this, we get both high quality constrained analysis fields that we can use for different scientific studies, but also can use initial conditions for ensemble-based forecasting. And I'll show examples of both of these in the sort of scientific results section of the presentation. So briefly, just the observations that we assimilate in the model. In the lower altitudes, we assimilate what would often be referred to as conventional lower atmospheric data. So this does not include satellite radiance data. So that's one thing that is missing compared to a modern numerical weather prediction system. But as I'll show on subsequent slides, we do a fairly good job of capturing the large scales in the troposphere. Then we assimilate some NASA research data in the middle atmosphere, temperature data from Aura MLS and Time Saber, which really helps to constrain the middle atmospheric dynamics of the model. And then at higher altitudes, we can assimilate the radio occultation, electron density profiles, ground-based GPS, GNSS total electron content, gold temperatures, and then icon MIDI, meridional, and zonal winds. And I'll show some examples of assimilating these higher altitude data later in the presentation. So here is an example, just looking at how well the model performs in the troposphere. On the right here is a snapshot at one time, comparing the NCEP, NOAA NCEP reanalysis geopotential height at 500 hectopascal compared to what we get from WACCM DART. And you can see there are some differences between these two. But in general, the large scale features where we have high geopotential height versus low tend to match between the, so here's the sort of high that we match with the reanalysis. And if you look at the structure, I'd say high latitudes in the summer hemisphere where we have low geopotential height match between the two. So we're at least confident that we can capture the large scale features in the lower atmosphere that are consistent with a reanalysis data product. So by being able to capture this, that means we can get at least the large scale flows right, and the sort of larger scale has a significant impact in terms of the mean state at higher altitude. So by capturing the larger scales, we can get most of the variability that then occurs at higher altitudes. So now I'll briefly show some results on looking at the sort of impact of different ways to assimilate the observations, different observations in the upper atmosphere. First, I'll focus on assimilating ionospheric observations using what we call an observation system simulation experiment. And this is a type of experiment where we essentially generate synthetic observations from a free-running version of the model that we consider the truth. And then by sampling that version of the model, we get observations and apply some error. to those observations and then assimilate them to see how well we can reproduce the true state of the model. So in this case, we generated a free-running truth simulation that had a solar flux of 164, and then we ran the data assimilation experiments with a sort of biased solar flux. So since the system is so strongly driven by the solar flux, having some bias there is useful in terms of seeing how well you can reproduce that. And because, as I said, there's a strong external forcing to generate sufficient sort of spread in the ensemble, we apply a standard deviation of 15 to this forcing from the solar flux, and then also perturb the upper boundary of the model to create larger spread, especially during the nighttime. And then we run 3 experiments. One where only the lower atmospheric data are assimilated. One where the ionosphere observations are also assimilated, but they only impact O+ in the model. And I should say in this model, the electron density is the sum of the ions. So by adjusting the O+, you're essentially adjusting the electron density in the F region. If you only adjust the electron density and not O+, it goes back right away. So that's why we adjust O+. And then the third case is also adjusting the neutral composition and temperature in the thermosphere to look at how, again, this sort of adjustment to the thermosphere impacts the state of the ionosphere in the short-term forecast. And then we assimilate all the observations hourly. So here's a snapshot at one time looking at the ground-based TEC observation. So on the left here is what we have for synthetic observations that are assimilated in the model at this time. And then on the right here, the columns are the different cases. So the left is with no ionospheric assimilation. The middle is assimilating ionospheric data, but only adjusting O+. And then the right is also adjusting the thermosphere state. And the top is the short-term forecast. So the 1 hour forecast. The middle is the analysis field, so right after assimilation. And then the bottom is if we difference the observations minus the forecast. And you can see on the left here, with no ionospheric data, there's a clear bias, especially you can see here over South America, between the synthetic observation that we're assimilating and the analysis. So it's clearly not capturing the state of the ionosphere by just assimilating the lower atmosphere data. And this is, of course, somewhat by design because of this bias in the solar flux. But if we do start to assimilate the ionosphere data, you can see that bias goes away. And if you look, it's hard to see here, but you'll see on the next few slides that are presented a more quantitative look at the errors. If you look at the observation minus forecast difference here on the bottom, for experiment 2 versus experiment 3, they are slightly lower. Say here over North America, you can see the errors are a little bit lower in this case when we adjust the thermosphere compared to only adjusting the ionosphere. So that would suggest that doing this adjustment to thermosphere state sort of improves the quality of the short-term forecast and also the analysis as well. And that's shown here more quantitatively. Here's the root mean square error on the top and bias relative to the TEC observations. So the gray line is if we don't do any ionosphere assimilation, and you can see it's quite very high root mean square error here. And assimilating the ionosphere data in black and red significantly drops that. And the black line here is when we only adjust the ionospheric state, and the red is also adjusting the thermosphere state. And the solid here is the short-term forecast, and then the dashed is the analysis state. And you can see in both the short-term forecast and the analysis, we get a much better, lower root mean square error when we adjust the thermospheric state as well. And it turns out this reduces the forecast root mean square error by about 17% and analysis by 12%. So we're getting a much better representation of the state of the upper atmosphere when we adjust the thermosphere as well, strictly from the ionosphere observations, of course. And the similar case for the bias, where you're really getting, the bias is lower when we account for the thermospheric state as well from the ionosphere observations. And that is for total electron content. We can do the same thing looking at, say, a fixed height. Here is 300 kilometers relative to cosmic radio occultation data. And the picture is the same, though it's a lot noisier when we consider sparser observations from cosmic relative to the ground-based TEC. But in general, you see the red line is always below the black line, indicating that adjusting the thermosphere gives you a better representation of the model state. One thing to note, however, is that this is quite highly dependent on where you are in the ionosphere and thermosphere. As I said, the system is still fairly sparsely observed. And in this case, since it's a so-called Aussie experiment, we know the truth. So we can look at places where we don't have observations and compare how the data assimilative model reproduces the ionosphere there relative to the true state. And here I just picked, these are time series over several days for a few different locations, one kind of in the middle of the Pacific Ocean, and then two in the Southern Hemisphere Ocean, where we don't have good observations as compared to, say, over the land masses. And for example, here, if we look at this location, if you look at the truth, which is in the dash black, and then the different assimilative cases, there's not much difference or improvement due to doing the data assimilation. The errors are shown here, and you can see they're quite similar for the different cases. So where we have poor observations, that's essentially important to recognize that the data assimilation is not always going to be as effective as you might want. Whereas if you look over, an area that's near some observations, like here in the Pacific, you still get some improvement from the data assimilation, but it's not nearly as good as you would get over, say, a land mass. So that's something to keep in mind with these sort of assimilative models. Is that the quality is still heavily dependent on what observations are going in and where you have observations. And finally, adjusting the thermosphere state also has a significant impact if you do an initialized forecast. So this is looking at where we basically just halted the model and ran a short-term forecast for 36 hours into future. This is just one forecast, so it's not entirely representative of a composite of several forecasts. But in this case, if we look at the no assimilation case, so this is root mean square error and then bias on the bottom relative to TEC observations. In the case where the ionospheric data are assimilated in the black line, we're just adjusting ionosphere, it essentially matches the control simulation with no ionosphere simulation at about 12 hours, where it's closer to, say, 16 hours if you have adjust the thermospheric state. So by adjusting the thermosphere, we also can improve the sort of short-term forecast skill of the ionosphere as well. By, again, I wouldn't say this is, in this case, it was 4 hours, but this is only one case. So, without doing a number of simulations and forecasts to really understand that, it may be more, it may be less than what is shown here. But I think the general behavior holds that by adjusting the thermospheric state, you're going to get an improved ionospheric forecast. And that was example looking at assimilating ionosphere data. We see something similar with assimilating the gold temperature observations. So here this figure is a bit, has a lot of lines here, but the green line is a run of WACCM that is essentially only constraining up to 50 kilometers. And then there's a few different data assimilation experiments. One where the gold temperature data were only used to adjust temperature itself, which is what you're observing. And that's experiment 1. And then experiment 2 is where we also adjust the thermospheric composition and then also the ionospheric state. And this is then the blue line is the ground-based GNSS TEC observation. And I should say this is real data, not a synthetic case. So we're looking at real observations here. And in general, you can see that when we do the assimilation, both cases get closer to the true observations themselves. And it turns out by adjusting the composition and ionosphere from the temperature observation, we get a much better agreement with the observed state. But in both cases, it's clear that they're better than the case in green, where we're not assimilating the gold temperature data. And I should say in this case, no TEC data was assimilated, just the gold data. And here's just looking average over time, where you can more clearly see the difference. So again, the red here is where we use the gold temperature data to also adjust the composition of the ionosphere and thermosphere. And you can see that the root mean square error tends to be lower in that case relative to if we just adjust the temperature or if we're not assimilating the gold data at all. And this is, again, relative to ionospheric observations. So even the observations from thermosphere really do have a significant impact on constraining the ionosphere in the model. And here the bias shows a similar thing, where using the gold data can improve the ionospheric bias relative to TEC observations over the American longitude sector. And the last part I will discuss here about looking at kind of implementation of the observations within the model is looking at the impact of localization of thermospheric wind observations. And here I use Aussie experiments to look at the impact of icon data, assimilating them using 2 ways. One, with a sort of standard localization function that is somewhat Gaussian-like. And then the other way is to assimilate them using what we call empirical localization functions, where we derive essentially the best way to assimilate and localize these observations. So here is example looking at these localization functions that we come up with. On the upper left here is around for an observation in the lower thermosphere. And you can see in the vertical direction, which is the y-axis, you essentially get something that looks Gaussian in altitude. So that would suggest that you can use this sort of standard localization. But if we go to higher altitudes in the thermosphere, for an observation in the thermosphere, you can see there's this sort of broad impact of the observations, especially to altitudes that are higher in the thermosphere. And this is kind of consistent with the fact that the winds in the thermosphere are not changing much with altitude. So by assimilating using this, we would essentially be able to take the observations and extend the impact in altitude that they're having, compared to just using a localization that would be confined sort of close to the observations. But in this case, right, we don't want to just do something very broad, because there's less correlation with lower altitude compared to above, so that you need a sort of asymmetric shape that comes out of this localization function. And when we assimilate the data with this, here is the root mean square error. Black is without the icon data, then blue and red are with, but with assimilating in different ways. And if we assimilate the data, it's kind of optimally, we get a reduction in the root mean square error of about 12% on average over a roughly 1 month time period. And if we then go a bit further and look at how, since the winds are going to have significant impact on the plasma drift, we can look at how this really has an impact on other properties of ionosphere. So here's the vertical plasma drift. In truth, this is day versus local time. And then here are the differences from assimilating icon data sort of optimally, difference with the truth, and then without the icon data. On the right, you can see that there's clearly larger errors here, especially during kind of the morning, relative to the truth in this case versus this case. And if we look at now on the right-hand side, I show where we kind of don't use the optimal way of localizing the observations. And you can see the errors can be a bit larger relative to optimally assimilating them. So by coming up with a way to optimally assimilate these observations, then we can get a much better representation of ionosphere as well. And that's shown sort of quantitatively here, where we look at the root mean square error of the vertical plasma drift velocity for these three cases over time. And you can see the red line here, where we optimally assimilate the data, is significantly lower than the blue that uses this sort of more Gaussian-like localization. So by coming up with ways to sort of optimally put these data into the model, we end up having a much bigger impact on other aspects of the model as well. In this case, the zonal winds have a significant impact on the vertical plasma drift if we assimilate them in an optimal way. And now I'm just going to show a few examples of kind of applications of the whole atmosphere data assimilation model. First, looking at dynamics and chemistry of the mesosphere. And one issue that has been a significant issue in whole atmosphere models is essentially simulating the downward transport of nitric oxides during polar winter. And this is just an example of several different model simulations in the contour, and then the sort of pink line here is the observations. And the details are not critical here, but if you look at most of these models, you can see that they're not reproducing what you see in the pink line. So they're not sort of extending this as far down as you see in the observations. Here on the left, I should say, these are the observation, but they're not, the models are essentially not transporting this down as well as you would like. And these, I should say, are not data assimilative models. This is another example showing this. This is just temperature difference between the observations here in the upper left and different model simulations, where you can see there's a clear difference in the temperature structure in the model relative to observations. They have these sort of higher temperatures at a much higher altitude than you see in the model. And so this misrepresentation of the dynamics in the mesosphere could be responsible for why we get this sort of poor representation of the chemistry as well. So hopefully by improving the dynamics in a assimilative model, we would get a better representation of the downward transport of nitric oxide. And here is just showing, similar to what I just showed here, is altitude or pressure on the y-axis versus day of year on the x. And this is during sudden stratospheric warming, where we have this elevated stratopause following the warming, and you see it kind of descends downward in time after the warming. In this case, it descends much faster when we have the what is called the specified dynamics version of the model, where it's only constrained to a lower altitude. But when we assimilate the data in the model, this stays at a higher altitude for a longer period of time. And then this has implications for the chemistry. Here is the anode downward transport we see here in the specified dynamics, where we're not constraining the mesosphere with observations. It tends to be confined to a much higher altitude, as you see here, whereas in the assimilative model, you can see this sort of tongue stretching further downward over time, which is more consistent, again, with the observation. So by assimilating these data in a model, we get a better representation of the dynamics and subsequently the chemistry as well of the middle atmosphere. And from using this, we can look a bit, since we know that the model is getting a better representation of the dynamics, we can look to get a better sense of the distribution of nitric oxide. Here on the right is the nitric oxide from the model in the contour, the color contour, and then the observations are these sort of, I guess that's hexagon and square. And you can see that where the observations show higher nitric oxide, you see also in the model as well, and it's not longitudinally uniform. You can see there's regions with much lower composition relative to these regions where it's much higher. And we can do some analysis then on the dynamics that would lead to this. And to do that, we use these so-called Lagrangian coherence structure, which are essentially a barrier to the transport. And you can see these sort of ridges are these kind of, I guess you would call them pinkish dash lines here that are these barriers. And you can see they well confine this sort of region of enhanced nitric oxide. So it would appear that these, we can use the dynamics in chemistry then to get a sense of what is driving this downward transport. And here is just showing in more detail the same feature and how it corresponds to an enhanced temperature and a sort of downward flow. And if we look here in more detail as what is driving this, these plots show longitude versus time, so day of year versus longitude. And these are observations here on the left. The contour, the color contour is the NO mixing ratio, and then the dashed and solid contours are geopotential height anomalies. And you can see that the low geopotential height tends to correspond to regions where we have higher NO concentration. Both this is in the observations, and then if we look at the model, we see a similar thing where the model shows these sort of enhanced NO concentration where we have low geopotential height, and then a lower concentration where we have higher geopotential height. And then so from using the model, where we can get more information than just is present in the observations, we can look at how is the transport downward in a region where we have a maximum versus a minimum. And that is shown here, where we look at this sort of planetary wave ridge, where we have this sort of higher geopotential height versus the lower geopotential height on 2 dates. And here you can see that in a ridge of the planetary wave, it's essentially the transport is not nearly as strong as in the region where it's a trough. So we're getting much stronger downward transport and then higher NO in that region. So this just shows how you can use sort of better representation of the dynamics in chemistry through data assimilation to get some better physical understanding of what is really happening than what you could get from the observations alone. And last, I'll just discuss a study we did to look at initialized predictions of variability in the upper atmosphere during so-called sudden stratospheric warming events. And in this case, we did initialized hindcasts of the model, where we have a 40-member ensemble where we run hindcasts of the 2009 sudden stratospheric warming. And we initialized these on several dates during January and February. So the 1st, 5th, 10th, 20th, 25th, and then February 1st and 5th. I think this is typo. And these are then initialized from the analysis fields of the model. So we have a well-constrained initial state, and then we just run the model forward in time for, I think in this case, 30 days forward. And then the ocean, I should say, sea surface temperatures are specified to true values. So this has some, it's not a true forecast in that way, because we have some truth within the model. But to give some sense of sort of realism, we did use a persistence forecast for the solar activity rather than just using the known value. But in 2009, in solar minimum, the solar flux and KP were not varying that much. So a 27-day persistent forecast is actually reasonably good in terms of reproducing the solar and geomagnetic activity. And if we look at, this is again sort of altitude versus time. This is a temperature in the northern hemisphere polar cap. So what we would consider the truth is on the bottom right here, where again you see this same figure I showed before, where you have the stratosphere warming and a mesosphere cooling, and then this elevated stratopause following that. And if you look at these first two forecasts that we initialize on the 5th of January and the 10th, you essentially see no feature that is consistent with what we have here on the bottom right in the analysis fields. But if we look at a forecast initialized on the 15th, you start to see this sort of cooling in the mesosphere and a warming in the stratosphere consistent with what we have here. It's of course not perfect, but it gives a sense that you can forecast this variability maybe 10 days in advance or so. And then the later forecast on the 20th, you get a slightly better representation of this stratosphere warming and this sort of elevated stratopause that happens after the warming. So this would suggest that we can then forecast, something like 10 days in advance, this sort of variability in the middle atmosphere. And by using these forecasts, we can look at how the forecast skill varies with height. In this case, I'm using the so-called anomaly correlation coefficient to look at how well the forecast performs as a function of forecast day. And this is for all of the forecasts together, not just the ones that are forecasting the stratosphere warming. But you can see in black here, which is in the stratosphere, it has a much longer, essentially it's the correlation is decaying slower, which would indicate a longer forecast skill in the stratosphere. And as you go to higher altitudes, you're essentially just shifting this way. Whereas when you get to the mesosphere, the dashed red and black, your forecast skill is significantly shorter than in stratosphere. So by doing these initialized forecast experiments, we can look at how forecast skill would vary with height. And the higher altitudes, you end up with a much lower forecast skill that may only be a few days relative to what you would get in, say, the stratosphere. And we can also predict a lot of tidal variability if we can capture the changes in the stratosphere and mesosphere mean state. Here is a look at a similar sort of structure where we have the different hindcasts initialized on 5th, 10th, 15th, 20th, and 25th of January, and then the analysis fields, which we consider as truth. And you can see roughly on the 15th and 20th, those hindcasts, we start to predict features that are seen and consistent with the analysis field. So again, we can predict these sort of tidal features a few days in advance of the stratosphere warming. And as these drive a lot of the ionosphere variability, we can look at whether we can predict what's happening in the ionosphere during this stratosphere warming. And here on the bottom right is the analysis total electron content. And you can see around the stratosphere warming, which is the dashed black line, there's this minimum in the total electron content. And in these hindcasts initialized, say on the 15th of January and 20th, you get this sort of decrease around the warming. It's not entirely consistent with the analysis, but you can capture some of this decrease and subsequent increase in the ionosphere prior to the warming. So that would suggest, at least during solar minimum and solar quiet time periods, you may have some forecast skill in ionosphere extending to at least several days. But this is, of course, one case during an extreme forcing from lower atmosphere. So really quantifying this predictability of the ionosphere driven by lower atmosphere, I would say, needs to be looked at in much more detail. And finally, just to conclude, whole atmosphere data assimilation, I think, presents a lot of unique challenges compared to looking at data assimilation in lower atmosphere. And we've addressed some of these, though certainly not all, to implement data assimilation in WACCMX. And I gave you at least some example of different scientific questions that can be addressed using a better constrained state of the atmosphere, as well as for initialized prediction studies. And of course, we're continuing to work on improving the data assimilation by improving impact of existing observation, and as well as adding new observations as well. And so thanks everyone for joining, and I'd be happy to take any questions that you might have.
All right, thank you very much, Nick, for a very interesting talk. Do we have any questions for Nick? Brian Harding says, could you say a little more about how the ELFs were derived?
Yes. So those basically look at, you run a case where you have a known truth, and then you basically assimilate the data and look at the root mean square error of assimilating the data, where you have the truth data known, to essentially derive a function that's going to have the most impact when you assimilate the data in subsequent. So we sort of run through once, assimilating the data with a sort of Gaussian-like localization function, and use that to get these sort of ELFs that we then use later on. So it relies a bit on having a known truth state.
Great. We have a question from Claudia as well. Feel free to unmute as well. I should have mentioned that earlier to ask your question. Okay. Claudia, I see you're unmuted, but I can't hear you yet. Okay, I can ask real quick. Thanks for a really nice talk. What is your approach to assimilate TEC when the model does not reach up to GNSS altitudes?
So in this case, we essentially just apply a extrapolation above the top. And I should say, in what we assimilate now is just a vertical TEC. So it's not slant path. So since it's just strictly vertical, we just extrapolate above the model top some, using the scale height to get an extrapolation of the model TEC that then we add on this sort of part that's extrapolated above the top, which of course has some, there's an approximation there that is not perfect. But with a model that doesn't extend high enough, that's sort of best we can do to make use of all the TEC observations that are available.
All right, thank you. Zue, you can feel free to unmute to ask your question. Otherwise, I can read it out.
Yeah, Nick, thanks for the talk. I just wondering if you have tried neutral density in your DA system and see if that worked. It just, I've been pushing a lot of neutral density measurements. And the second question is, what's your opinion? What would be the best thermosphere parameter for, in your opinion, that does the best job for ionosphere thermosphere forecasting?
So the thermosphere density we have not done in WACCMX with Dart, but I know that's been done in TIE GCM with Dart, so it would not be too difficult to do. So there's no sort of inherent issue of doing that. So that, I think, answers your first question. One issue with that data is, depending on how you do the assimilation, the way we're doing it, where we just adjust the state, the impact will be quite small because you just sort of have, single satellites in a path. Unless I think the best way to probably assimilate that data is also adjust some forcing parameters as well. And then in terms of the best impact of the thermosphere on the ionosphere, I don't necessarily want to speculate on that. I think this is really where you can use a data assimilation framework or do experiments to test that, would be my opinion. I think just kind of trying to guess at what would be the most impactful thing to say observe or adjust in the thermosphere to improve the ionosphere, there's no reason you can't do experiments to find that information out rather than just speculating. So that would be my opinion on that. Obviously temperature and composition have impact, but relative which has more, I don't know. And I think that's where doing some initialized forecast experiments where you're adjusting different things can really give you that information, and then it can be used to either design new observations or come up with the best way to use ionosphere data to adjust those states.
Thanks, Nick.
Awesome. And I actually have a quick question. Is early on you were talking about doing your ensemble propagation, and coming from a geospatial modeling background, that sounds very expensive to me. So can you talk about how you balance the number of states in your ensemble versus the grid resolution and the degree of the physics that you're evolving in your simulation?
Right. Yeah. So that's of course the downside of the ensemble approach, is that we usually use 40 ensemble members, which essentially means that you're running the model 40 times in the forecast step. So it does become expensive. It's not prohibitively expensive, I would say, right? Like we've done experiments for over a year and things like that. So it can be done, but it does require supercomputing resources to do those sort of simulations. So that's one thing. And ideally, we would probably actually want maybe 60 or 80 ensemble members. 40 is a kind of low number if you talk to other people. So, but that's this just balance of, you can't really have it.
Yeah, there's only so much
because it's just too expensive to run for long time periods. And same with grid resolution, right? We run these at roughly 2 degrees, whereas there's version of the model at 1 degree is maybe better, but to do the assimilation, you're increasing the cost a lot. So there's
right, yeah. So in that case, it's more worth it to have the extra ensemble or extra number of states per ensemble than the extra resolution.
Yeah, exactly. There's a bit of a balance there of how best to do it.
Yeah, that makes sense. All right, awesome. Thank you. Are there any final questions for Nick? All right, seeing none. Thank you once again for a very interesting talk. I learned quite a lot. I hope everyone else did as well. And thank you. And please check the website for updates and your emails. You can subscribe to the mailing list to the website for future updates on our next seminar. Thanks very much, everyone.